enough about Atlanta. So today we will have so first off, I was thinking about doing a quiz on, an in-class exercise to help you guys better understand trees. But I feel like that's better pushed. That in-class exercise that I have in mind, which is doing tree rotations, is actually better pushed off until Monday, until I can make sure that everybody has got a good grasp of the basics for trees. And so this today will be a overview of a question I do like to ask on the first exam, which is, given a list of numbers, please construct a tree from these numbers that I add you, that I give you, okay? And then I'll typically say either, given this tree, remove these numbers from this tree, or you just drew a tree, so now remove these numbers from it. So I'm going to go over the add and remove method for a binary search tree. Now, remember, the difference between a binary tree and a binary search tree is whether or not, we keep a particular property. What is that property? What makes a binary search tree a binary search tree as opposed to a binary tree? Any takers? Yeah.
Is it order?
Yeah, the order. The fact that we maintain order. How is order maintained in a binary search tree? So suppose the value of the root of the tree is 10. How would things be ordered in this tree? Oh, all the way in the back.
Everything to the left would be lesser, everything to the right would be greater than that.
Yep, so everything over here is, and I'm going to draw a symbol, a triangle, and that's just simply meaning there's a giant tree here of indeterminate size. Everything in this subtree is less than the root, so less than 10 in this case. Everything over here is greater than the root, right? And this property is recursive, meaning that basically if we have a root, there's a root of this subtree over here, and everything less than it goes to the left of it, everything to the right of it goes to the right of it. So let's start out with just this single tree, and we're going to start adding things to it. Now, a very simple algorithm, it's the zigzag algorithm I've described, which is you basically go left if you're less than, right if you're greater than, and once you hit the end, once you find what you're looking for, you just stop, okay? Now, when you're adding, what you're looking for is an empty space to put a node, right? So let's go through this. Suppose I wanted to add the value 7 to this tree. What do we do? Anyone? Right, values to the left, values that are less than go to the left. So we go, okay, we want to add 7 to this tree. 7 is less than 10. Okay, so we go to the left subtree. Okay, the left subtree is empty, so we just simply stick 7 right there, right? It's a fairly straightforward process. All right, somebody else choose a number, and let's keep it under 100, shall we? Anyone? Yes? 12. Okay. So to add 12 is greater than 10. So we go to the right, and we put 12 over here. Okay? Next number. 9. 9 is less than 10, right? 9 is less than 10, so we go to the left subtree of 10. 9 is greater than 7, so we go to 7's right subtree. So we add 9 over here, right? Go left, and then you go right? So again, with recursion, the big thing is that we look at every step locally. Like, do I go left here or right here? I don't look at the whole thing. I just go like, I'm here now. Do I go left or right? Right? Or am I done? All right, another number. Anyone? 2. Okay? 2 is less than 10. 2 is less than 7. So we place 2 over here. Another one. 15. 15 is greater than 10. 15 is greater than 12. Another? 13. 13 is greater than 10. 13 is greater than 12. 13 is less than 15. So 13 ends up over here. 11. 11 is greater than 10. 11 is less than 12. So does everybody kind of have understand how like the add algorithm works here? It's a fairly straightforward algorithm. You go to the left, you go to the right. Now homework, you're going to get the chance to implement it, although that really shouldn't be too hard because, if you look at your textbook and your slides, you've been given the code for that, right? But you'll have the chance to implement it for yourself in the tree homework. And it just takes some slight modification. Now, remember, we're dealing with numbers here, but it could be anything that's comparable, right? But for the sake of simplicity, because we're really good at telling if numbers are what order numbers go in, we use numbers as opposed to things like strings, right? So, all right. So adding is fairly straightforward. You start at the root, and then you go left or right, depending on whether you're less than or greater than, respectively. And once you hit an empty spot, you just simply create a new node. And the way we do that in the code is you return yourself to the person who called you to say, hey, attach me to you as your child, right? Now, deleting is a bit different. Deleting, the way we know we're done is that we get to an empty spot. So say I want to delete 1 from this tree. 1 is less than 10. We got to find 1 first. 1 is less than 10. 1 is less than 7. 1 is less than 2. We hit an empty spot. That means 1 is not in the tree, right? If 1 is in the tree, we would have hit it because everything would have been in order. So 1's not in the tree, so we just tell the user that they messed up. 1 isn't in the tree. Can't delete it. Okay. Okay. So that's base case 1. Okay. The recursive cases were me going left or right. Is my thing. If the thing isn't equal to the number I'm looking for, I go to the left or I go to the right. Those are the recursive cases. The recursive cases are easy. You just simply say delete this 1 from my left subtree. And then 7 says delete 1 from my left subtree, and 2 says delete 1 from my left subtree. And this says, well, I can't boss, and that says I can't boss, and that says I can't boss, right? So the other base case is actually the complicated part. It's only partially complicated, okay? And that's if we hit the number we want to delete. So there's 3 cases we have to be aware of for deleting, okay? 2 of which are super easy to handle. The first case, if we want to delete something, is we delete a leaf, is deleting a leaf from the tree. Right? Suppose we want, and reminder what a leaf is on a tree.
The end, like the last one?
Yeah, how would I know if it's a leaf?
If it doesn't have any branches off it.
Yeah, if it doesn't have any branches off it. I saw your hand too. Okay? What do you know what non-leaves, what would you call non-leaves? No, not branches. Sorry. Internal nodes, right? You can call them internal nodes. You can also call them non-leaves. The terminology here is actually very fluid, right? You can call these things branches or links, right? You can call, say that 9's parent is 7 and its grandparent is 10, even though grandparent isn't a formally defined term. Everybody's going to understand what you mean, so everybody uses it anyway, right? If we want to delete 9 from the tree, all we have to do is because 9's a leaf, just deleting it causes no issues. It doesn't reorder anything in the tree. It's just gone. That's easy. Deleting something that's a leaf is super easy. Okay. Say though that we wanted to delete 7. Okay. 7 in this case now has 1 child. That's also fairly easy. Right, we have to delete 7, but we need something to take care of 2. And so in that case, what you do is that you just simply let your parent adopt your child, right? So if we're deleting 7, all we have to do to handle that is just simply make 2 10's child, right? On the other hand, say that we had 7, what was it? It was 7, and it was 9 over here. Suppose that we want to delete 7 this time. Again, the same rule applies. We would just make the single child the same child. And notice that I would make the single child my parent's child. And notice that the tree is still in order, right? It hasn't affected the order of the tree. Okay? Well, let's go ahead and reset and make this a bit more complicated. So I'm going to put 8 here and 9 here. And I'm going to put 2 here. Okay, so I've just inserted 8 and 9. Okay? Now, suppose that I wanted to delete 10. I wanted to delete 10. And this is where we get into our more complicated case. And the way you'll see that we handle it is that we reduce the complicated case into an easy case. Okay? We take something complicated and we go, oh, complicated stuff that's hard, we'll just turn it into one of the easy cases with a bit of thought. So the issue, and the primary issue with deleting something with 2 children is that what's supposed to become the new root of the tree, right? You can't move 7 up because it has this entire branch over here that needs to be taken care of, right? And you'd have to do a lot of work to like move, you know, if we move 7 up, then we have to move 8 and 9 over into this branch, you know, into this subtree over there, and that's just a lot of work, right? So we want to choose something that would make it really easy to reorder the tree. Can't choose 2. And the values that, if we look at the tree and just try putting each value as a new root, so moving 2 we don't have to reorder, we'd have to reorder everything. Moving 7 over, we'd have to reorder everything. Moving 8 over, we'd have to reorder everything. But if we move 9 over, we don't have to reorder everything. If we move 11 over, we don't have to reorder anything, right? Just if we take this value, put 9 over here and deleted the 9 down here, we wouldn't have to reorder anything. We took the 11, moved it up here, we wouldn't have to reorder everything, right? The value, that would be the only thing that would have to change. 12, 15, and 13, same problem as 2, 7, and 8. We'd have to reorder a bunch of stuff in the tree. And if you notice that if we do an in-order traversal of this tree, in other words, we go through this tree in order, right? We start at the root, we print out everything in the left subtree using the in-order traversal, print out myself, print out everything in the right order, right subtree using in-order traversal. In other words, right, do my left subtree, this says do my left, so print out 2. It says I'll print out myself, print out my right, print out my left, that's nothing, print out myself, print out my right, print out my left, that's nothing, print out myself, print out my right. Then then we go back all the way up here, print out myself, and so on and so forth. It will print out in order. So if we notice what's special about, if we print out all the values in the tree in order, well, we notice that what's special about 9 and 11 is that they come, they come right next to 10. So 9 is what's called your in-order predecessor, and 11 is called your in-order successor. And so you just choose one of those to replace it. And by convention, I always choose the in-order predecessor to replace my when you want to replace your root. Now, how do you find your in-order predecessor? That seems like it's really hard. Turns out it's not actually that hard. If you want to find your in-order predecessor, well, first off, it's going to be less than you. So you're going to find it in your left subtree, no matter what the value is. You're going to find it in your left subtree, right? Because your in-order predecessor, the thing that comes before you, it's going to be less than you. Okay? So you step to the left and get into your in-order and to get into your left subtree. And then to find the biggest thing in your left subtree, you just go all the way to the right until you can't go further anymore. That's guaranteed to be the biggest value. Why is that? Well, if you go left, that's a value that's smaller. And if you keep going right, if there was another right value, that would be bigger, and that would be the biggest value. If there's no value there, but say there was a value over here, right? Well, that would be smaller than this, right? So by going all the way to the right, you're guaranteed to hit the smallest the biggest value that's smaller than you. So okay. So now, how does that work in practice? Now that we know how to find that guy, what we do is we find our in-order predecessor, go to the left, all the way to the right. So basically, zig and then zag as hard as you can. Copy that over into the root, right? And now we delete this guy. Now, because we went all the way to the right, we're guaranteed that this guy over here is going to either have no children, in which case it's pretty easy to remove him because you're just deleting a leaf in that case, or he's guaranteed to have a left subtree. He'll have a left subtree. In which case, again, you're just deleting a thing with a single child. So all you do is you have the biggest, your in-order predecessor's parent adopt that. And that will maintain the order. Right? So we just reduced the deletion case, the hard deletion case, to copy over the value of the biggest thing and then go back to one of the easier cases. It's always guaranteed to have no children or one children, because if it had 2 children, well, then we'd still be able to go to the right. So once we stop going to the right, we found the biggest thing. So it's always guaranteed to find the biggest it's always guaranteed to find the biggest thing. So we deleted 11. So let's go ahead and see what happens when we delete 12 from the tree, right? 12. If we want to delete 12 from the tree, right? We work from this subtree, and we want to delete the in-order predecessor. Sorry, we want to delete 12, so we find the in-order predecessor. Sorry, I'm just trying to get back into this. So we go into the left subtree, and we find the biggest thing in the left subtree. So we go to the left, we go as far as we can to the right, which turns out to be nowhere, right? So we copy the value over and delete the in-order predecessor. So that's just deleting a leaf. Okay? Let's go ahead and look at, let's see. I want to make this a bit more interesting. So let's go ahead and look at deleting, let's go ahead and add 6 here, and add 5 and 4 over here, right? So let's look at deleting 7 from this tree, okay? So we're deleting, so we start at the root, we go to the left because we're trying to delete 7. We go to the left, we find 7, so now we want to delete 7. So we have to find the in-order predecessor, which is the biggest thing in the tree that's smaller than it. So we go to the left, and then all the way to the right, we found it. We copy the value over to the root of the subtree we're trying to delete. And now we delete this guy. He has 1 child, right? He has 5 as his child, right? And never mind that 5 has his own, child. That we don't care about that. 5 has, 6 had 1 child, which was 5. So we have to adopt 5. Right? And it maintains its order by doing this operation. Make sense to everybody? All right. So the quiz that is today on trees is going to be of the following format. I'm going to present you with a picture of a tree and ask you to add something to it. And there's 4 options, right? There's 4 very nicely drawn options. I spent like a couple hours back in spring rendering them in LaTeX. You choose I give you a tree, I give you the before picture, tell you to add something, and you select the after picture, okay? Same thing with delete. I give you the before picture, the before tree, I tell you to delete a node from it, and I give you the after, and you got to select the after. Does everybody feel like they can do that now that you've seen me run through this? All right, so let's go ahead and give that a try.